Hello, everyone. Good afternoon. My name is Daniël and Wolde. I'm a master student doing my project at CWI Database Architects Group. It's on integrating SQL PGQ in DuckDB. And I did this together with Tavneet Singh and Gabor Sanyas and Peter Bonks as my advisor. So I don't think I need to explain too much, but SQL PGQ is going to be part of the upcoming SQL 2023 standard. It's a read-only version, where graphs are defined in terms of tables. And the queries contain special syntax. So what's really unique is the pathfinding and the pattern matching in SQL PGQ. When I made these slides, I was still under the impression that the cheapest path was going to be in. But upon coming here, I heard that it's pushed to a later version of SQL PGQ. Still, it's part of what we implemented. And as a quick example, for the SQL PGQ, you create a property graph in terms of vertex tables. So a person who has properties of person ID and the first name, and the university who has the university ID and name. And then there are the edge tables. In this case, we have a nose table who, as a source, has a person, destination, another person, and the creation date as a property. Same goes for the study at, which has a source as the person, and it goes to university with a study year. And then if we want to select, we have this graph table where we have a person one who follows a nose edge to a person two. This person two studies at a university. We can filter it. The first name has to be Daniel for this P1 node. And the university where this P2 is studying at is the University of the Universiteit van Amsterdam. We then select this person to his name and the year he started to study. So yeah, the goals we defined when starting this project was to provide an open source implementation of SQL PGQ. And I do this as part of my master's thesis, where I focused mainly on the pathfinding algorithms. We used multi-source breadth-first search for the shortest path and a batched Bellman for the cheapest path. And I'll go into more detail on this later. There were some challenges that a graph database management system should provide a superset of the features. So we had to build on top. We built this on top of a relational database management system. We needed efficient shortest path and cheapest path algorithms, and in the case of SQL PGQ, it's common to have a many sources to many destination queries, which is important for the algorithms we selected. So to introduce DuckDB, it's developed originally at CWI. It's now a spin-off company. It's open source in process SQL OLAP. So it's for analytical purposes mainly, database management system. It has over 100,000 monthly downloads, 5,000 GitHub stars, and 500 forks. And I was not paid by DuckDB to say this. The parser is based on the Postgres parser, and it's a stripped down version. And to support SQL PGQ, we needed to make changes. We need to add keywords. There's no way around this. It has a vectorized execution engine, which is the specialty of the CWI, with Vectorize having the same execution engine previously. And it allows for scalar user-defined functions, which can handle the parallelization of these functions for you, if done correctly. And we will use this to create a lightweight implementation for the functions, where we don't need to change too much to the internals of DuckDB. And lastly, DuckDB allows for extension modules, which can be turned off and off, on and off pretty easily. So we don't necessarily need to change the mainline DuckDB. And now to create a bit more behind the scenes, we change our graph into a compressed parse row data structure. This is done on the fly for every query. And it's a compact structure with good locality, which is good for the scans. And it's a little bit difficult to explain, but essentially there are two arrays. One is the vertex array and one is the edge array. In the vertex array, at the position of the vertex ID, we store the offset at which the outbound edges can be found in the edge array. So in this case, we highlighted node 4. And in the vertex array at position 4, we see the offset 6. And at position 6, we see the node IDs 1 and 3, which correspond to the outbound edges of node 4. And this way we create a really compact structure in which we represent our graph. The alternative would be a pointer-based system, but that would get inefficient once you do multiple hops due to the cache misses. And this way you can minimize that. For the shortest path, we realized that it was inefficient to execute these shortest path one by one, so one source to one destination. So we needed a batch solution to amortize the cost, because we have typical many source to many destination queries. And with the solution we found, we have the ability to share the memory access, which is a major bottleneck. It's not the computation that's per se heavy, it's the memory access. So we came to multi-source breadth-first search, the one developed by Manuel Tain. It was published in a VLDB paper in 2014. And it essentially works like regular breadth-first search, but we have multiple running at the same time. This way we can share the memory access. And importantly, it can also make use of SIMD instructions, such as the AVX 512. I have a simple example. Oh, these are the old slides. Okay. We start from, we have two BFSs running, one from node 1 and one from node 2. And in the matrix, we see B1, which corresponds to BFS1, and B2 corresponding to BFS2. In the next step, they each explore their neighbors, which are node 3 and 4, which are then added to the visit node and to the scene node, but to the scene matrix, sorry. And then in the next step, from node 3 and 4, they explore their neighbors. For BFS1, it still needed to explore node 2, and for BFS2, it still needed to explore node 1. And they also both simultaneously discover nodes 5 and 6. Now they realize that there are no more edges to be explored, and the algorithm terminates. We had a similar implementation for the cheapest path. We used the batch Bellman Ford, also by Manuel Tain. It was published in the BTW paper in 2017. And it can also make use of SIMD instructions. I thought it was going to be short on time, so I won't dive into too much detail, but you can find it in this paper. To evaluate our implementations, we used queries from the SNB interactive workload. One is query 13, which is just a simple person 1 to person 2. And we need to find out whether there's a nose relation between them. It can be 0 to many hops. In this case, we have a large search space, which we can't filter out on. So there are a lot of possible edges. And we can use MSBFF for this, since it's an unweighted file in this case. Here we see the total runtime. This includes both the CSR creation and the pathfinding. We did about 400 path queries, or we discovered about 400 source destinations per skill factor. At the top, we see skill factor 10K, which took a little over 1,000 seconds. It's not quite linear scaling, and the number of edges was about 300 million in scale factor 10, in scale factor 10K. I do need to mention we used a relatively old version of DuckDB, version 0.2.2. Currently, it's on 0.3.4, which is about 8 or 9 months further into development. It's currently in very active development, so with each version, queries get faster and new stuff gets implemented. So it could be that if we update to the newest version, we see a performance increase. Here we see the relative time where we spent on each phase of the query execution. The most important bits are the red areas, which is the creating the CSR, and the yellow area, which is the actual MSBFS in this case. We see that for the larger scale factors, the CSR creation starts to take more time relatively to the pathfinding. And we also see that finding the path options refers in this case to we store them in an intermediate table. And this is this takes more time relatively in the smaller scale factors. The CSR creation and pathfinding can be further optimized possibly. So that's something we're looking into. For the cheapest path, we use BI query 20. It was explained yesterday briefly. But the most important part is that we're given a company and a person 2. And we need to find a person 1 who shares a connection with this person 2 and works at the company. And the weight between person 1 and person 2 is, well, they first need to know each other and they need to have studied at the same university. The weight of the edge is then the absolute value in difference between when they started studying. In this case, we do pre-compute the edge weights, and we can prune the number of nodes and edges, which reduces our search space. But still, performance, it's not that great. We could only so far do up to scale factor 100, which took over 10 hours to complete. So yeah, we need to look further into this. And if we look at where the relative time is spent, it's dominated by pathfinding. The CSR creation isn't even showing up in this case. And yeah, so the pre-compute does take a little longer for the smaller scale factors, but it's heavily dominated by the pathfinding in the larger scale factors. So to conclude, DuckDB is an ideal candidate for the SQL PGQ implementation. It's lightweight using the scalar UDX. Scalability of the batched algorithms is promising, and we can further optimize it using CMD instructions and other ideas we're currently exploring. Thank you for your attention.
Daniël, it seems there are online questions. So Domagoj, please go ahead.
Okay, thanks. Hey, Daniel, thanks. Very cool work, actually. I like it a lot. So I have a lot of questions. I'll just ask some very direct ones here. So do you support returning paths?
Yeah, we should support, for the shortest path, we can return the path.
But just one shortest path between 2 nodes, right? Not all shortest paths between them.
All shortest paths.
Okay, cool. And okay, second question. So you assume that everything fits in memory, right? In RAM for this to work?
Yes, in this case.
Okay.
Yeah.
Cool. And the last thing, does DuckDB get any benefit from parallelization? Because you have a machine with like 1 million cores and everything. So is this even affected, or the algorithm is just linear and doesn't care that much about it?
Sorry?
The machine does not have 1 million cores. It has.
Okay, it's not 96. No, that's for me.
96.
But that's
Yes.
96 more than the one I ever used. So, you know.
Yeah, so DuckDB spawns another thread for every about 100,000 rows. And I need to look further into whether that's how much that impacts the pathfinding.
Okay.
That's something we'll
But so
look into.
you think there is something at least with this? It gets like, okay, cool. Thank you.
One question from the room from Bailey.
So, so if you use the DuckDB's existing storage, what would be the bottleneck?
That's a good question. I'm not sure for the answer, if I'm very honest.
Really, what is your definition of existing storage?
So like just whatever it has right now, like maybe a kernel stuff in memory. So if we just use that to do this algorithm, what would happen?
Instead of using a CSR? you mean?
Yes, in memory cache.
Well, there is no such thing as an existing algorithm because, well, I like to say to every native graph vendor that navigation is a join. So, and I will repeat that. So, but then again, I mean, if you would want to use join, so like say the algorithm usually used in DuckDB is the hash join. So you could imagine instead of using a CSR to create a hash join that maps vertices into edges. And you could imagine then running an algorithm like even MSBFS on that, but you would have to implement that algorithm as well. You know, it's not like something that you would easily describe in SQL. We, by the way, know since yesterday that it is possible to describe this in SQL because this is the way that Umbra handles this. I personally think that without JIT code generation, that will never be acceptable in terms of performance because of the interpretation overhead. So I'm kind of struggling to answer your question because you seem to say, okay, so what if instead of a CSR data structure, you would choose to create a hash table? It would be significantly slower because, yeah, maybe twice slower probably or something. I think because you will be dominated by cache misses. The hash table will have cache misses. This CSR structure has some cache misses, although the access pattern of these algorithms is very sequential, which is nice, both in the vertices and in the edges. So yeah, maybe it's actually more than, it will actually be more than twice because this algorithm, because the hash table will also lead to a random access pattern, and this actually gives you sequential access patterns. So it's an interesting question, but given that we would have to implement that as well in terms of a new algorithm, why would you do that? Is that the question? If you can also create a CSR.
Right. So I was asking because, you know, if you start to do CSR, I thought there was default implementation, it didn't work quickly enough, and then we do something more efficient. But I think this is good.
Yeah, no, we went immediately for the solution. Of course, we have also thought about okay, how to make CSR creation fast. And one of, I mean, normally you would have to do things like group by, distinct, and then twice a join. So you would go for the edge table and you would join it twice to the vertex table in order to kind of map source and destination edges into numbers, because that's what you need to do to create the CSR. Yeah, and we are exploiting row IDs heavily. So there is no sorting, no real grouping going on. This is mostly a sequential scan on the edges, or two of them actually. But so it's relatively fast, and it should also be parallel. All of this should be kind of multi-core parallel out of the box.
Okay.
So maybe to hijack, just sorry, in my talk, I'm gonna try to answer Way's question more directly and maybe contradict Peter a bit, but you can see that later.
That's what this workshop is for, to discuss ideas. One question from Oscar online.
Yeah, coming back to that earlier question about returning paths, like what kind of structure do you return?
We return a list of all the nodes that are on the path. So starting from the source to the destination.
Like a vertex, like IDs or something of the nodes, or you have actual, okay.
And then that is using the list type of
that's using the list type of
because DuckDB supports list and nested structures.
Yeah.
Okay. And the other question was, I saw you were comparing the creation of the CSR to like the pathfinding, but normally the CSR is only created once, I assume. Whereas pathfinding then happens like many times. So normally you don't really compare these two, but I guess I was just wondering, like, is the reason you're comparing it is because you expect you need to create a CSR every now and then when there's a batch update or something?
So we took the decision to create a CSR for every query. So it's on the fly. Instead of creating it once, whenever the graph table, I guess, is created.
Okay.
So yeah, that's why
I didn't realize that. And wouldn't it make more sense to create it once and then reuse it for queries?
Perhaps that's something we can explore, but the relative time to create it is not per se necessary. Also, whenever you have an update, and if you have frequent updates, you would need to recreate it very often because it's not very easy to update the CSR. You would have to recreate it from scratch, basically.
Yeah. Okay.
That's why we took that